Welcome to the deep dive. Today, we're digging into the core architectural notes on the philosophy behind the GrapheneOS operating system.
Right.
And if you're coming into this thinking GrapheneOS is just Android without Google, you're about to find out it's something much, much deeper.
That's really our mission today, isn't it?
Yeah.
To get past that surface level idea, we need to establish what GrapheneOS truly is. A hardened operating system.
Hardened?
Yeah, engineered from the ground up to resist very sophisticated, even state-level attacks.
And the core thesis from the sources, the idea that underpins everything else, is that you just cannot have real privacy if you don't have security first.
Exactly. I mean, think about it. If an adversary exploits your phone, if they can run their own code on it, what good are your privacy permissions then?
They're irrelevant.
Completely. If they own the device at that low level, they own all your data, period.
Which I think brings us to a really crucial distinction we have to make at the start. Security versus privacy. They're not the same thing.
Not at all. Privacy is about data control. The question is, who has access to my data? Stopping an app from seeing your location. That's a privacy control.
Okay, so security is what?
Security is about the device's integrity. It answers the question, can an adversary run code on my device without me knowing?
Right, so like stopping a malicious PDF file from completely taking over your phone just because you opened it.
That's the perfect example. One is about protecting data, the other is about protecting the device itself.
Okay, let's get into the architecture. GrapheneOS isn't a fork in the traditional sense, is it? It's based directly on AOSP.
Right, the Android open source project. It's more like they take that core, that foundation, and then they apply this massive patch set of security enhancements right on top.
And where do they start? What's the first step in that hardening process?
The first pillar is probably the most elegant. Attack surface reduction.
Meaning?
The philosophy is just incredibly simple. The most secure code is the code that isn't there.
So you just
You systematically remove things that aren't absolutely essential. Old hardware drivers, legacy network code, anything that could be a potential entry point for an attack. You just get rid of it.
less code, fewer potential bugs to exploit.
Exactly.
So that leads to the next pillar, which is really proactive. It's called exploit mitigation.
Right, because the GrapheneOS team assumes bugs will happen. It's software. Vulnerabilities are, inevitable.
So the goal isn't to be perfect, but to make those inevitable bugs almost impossible to actually use against you.
Yes, and one of their crown jewels here is replacing the standard memory allocator with something called a hardened malloc.
Okay, what does that do in plain English?
Well, normally an exploit needs to know exactly where to jump in your device's memory to take control. The standard allocator can be predictable.
And the hardened malloc just randomizes everything.
It adds randomization and a whole bunch of extra checks. It makes those common memory corruption bugs like a heap overflow incredibly difficult to turn into a working exploit that actually runs code.
They also have this thing called exec spawning.
It's about isolation. It ensures that every time an app starts, it starts in a completely fresh, sterile process.
So if one app gets compromised,
The blast radius is contained. It can't easily bleed over into other processes because there's no shared state left hanging around.
okay. And the last pillar is network hardening. This has some features you can actually see and touch as a user.
It does. A big one is per connection M of tree address randomization by default.
Which means the Wi-Fi at your local coffee shop can't track your device visit to visit, right?
Right. Your phone looks like a new device every single time it connects. But the really unique feature, the one you won't find anywhere else, is the network permission toggle.
Ah, yes. You can install an app, and even if it asks for the internet, you can just say no at the OS level.
You can completely cut it off from the network. The app has no idea. It's a powerful user control.
So let's tie this all together for you. The core value of GrapheneOS isn't really the de-Googling. It's the enhanced resistance to zero-day exploits.
The unknown threats. The vulnerabilities that the developers themselves don't even know exist yet. That's what this is all built to defend against.
We've laid out this incredible software fortress.
But that's only half the battle. And it brings up a paradox the sources point to. If the software is this secure, why does it almost exclusively support Google's own Pixel phones?
That's the question we'll be tackling next time. It all comes down to the hardware foundation, Google's Titan M2 security chip, and a principle called verified boot. All right, let's dive in. Today we're getting into something really fundamental to modern digital security. We're talking about the idea that the hardware is the ultimate root of trust. And that leads us to a kind of paradox. The most privacy-focused operating system out there, GrapheneOS, runs exclusively on Google Pixel phones. For anyone focused on privacy, it just seems contradictory, right? Why Google?
Exactly. And what's fascinating here is that the reasoning is it's purely technical. It has nothing to do with brand loyalty. Our mission today is to show you why that hardware choice is basically non-negotiable. It really boils down to 3 specific security pillars that, for now, only these devices provide.
Okay, so 3 pillars. Let's break them down. What's number 1?
The first pillar is all about verified boot. But more specifically, it's the ability to relock the bootloader after you install a custom OS. Most other manufacturers, Samsung, Xiaomi, they either won't let you unlock it, or if you do, the security chain is just broken forever.
So you're forced to leave it unlocked. That sounds like a huge security hole.
It's massive. It leaves you wide open to physical tampering.
Got it. Okay, so what's the second piece of this puzzle then?
That ties right into the need for strong insider attack resistance. This is where a dedicated hardware security module comes in. It protects your encryption keys.
And it provides rate limiting. So wait, are you saying the decryption key isn't even stored on the main chip of the phone?
That's the whole point. If the key were on the main CPU, it could potentially be extracted. The security module, this separate chip, is what enforces the time delays between wrong password attempts. It makes a brute force attack, well, functionally impossible.
Okay, that makes total sense. Now the third one sounds a bit more complex. Proper IOMMU support. What are we talking about here?
So the IOMMU, that's the Input-Output Memory Management Unit.
Yeah.
Think of it as a bouncer for your hardware. It makes sure that every little component, like your Wi-Fi card or your cellular radio, stays in its own lane. It can't access memory. It's not supposed to.
And without it, they could launch what's called a DMA attack, direct memory access.
Exactly. A compromised radio, for example, could theoretically just reach over and read data directly from the main system memory. It could steal your secrets, and the main OS would have no idea it was even happening. The IOMMU stops that cold.
This is where it gets really interesting, because that hardware security module you mentioned, that's the Titan M2 chip, right?
That's the one. It's a physically separate, hardened chip on the motherboard. It is the ultimate gatekeeper of the lock screen.
Because it holds the keys, not the main processor.
Right. And because it's physically separate, it can enforce those rate limits we talked about. This is so important. Even if an attacker physically unsolders the phone's main memory chip, they can't decrypt your data. Not without the key from that specific Titan chip.
And that physical security is what enables the whole chain of trust, also known as verified boot. Can you walk us through that chain?
Yeah, it's like a series of digital handshakes. The first bit of code in the read-only memory verifies the bootloader. Then the bootloader verifies the kernel, and the kernel verifies the operating system. Each step checks the signature of the next.
Ensuring nothing's been tampered with.
Not even a single byte.
And this is where we get back to the key differentiator. Most custom ROMs force you to leave that bootloader unlocked, which breaks the chain. That leaves you vulnerable to that evil-made attack someone with physical access tampering with your device.
Precisely. And GrapheneOS is unique because it's designed to let you relock that bootloader with your own new keys. The moment it's locked, the Titan M2 takes over and enforces that signature check. If anything is out of place, it just won't boot. That's the gold standard.
So wrapping this up, what's the takeaway for you, the listener? It's that the hardware is the inescapable foundation. Running a secure OS on insecure hardware with an unlocked bootloader. It's like putting a steel door on a straw hut. The foundation is what matters.
To just quickly recap those pillars,
Yeah.
You need that ability to relock the bootloader, you need the Titan M2 to guard the keys, and you need IOMU to isolate all your hardware components.
Right. So we've locked the front door of the house by securing that hardware foundation, but we still need to worry about what happens inside the house. For your next step on this journey, we're moving up the stack from hardware to software memory. We'll be talking about how preventing memory corruption is the key to stopping most functional exploits.
Welcome back to the deep dive. Today we are strapping on our virtual helmets. We're going straight into the runtime security environment.
And our mission really is to unpack the single biggest source of software bugs out there.
Memory corruption.
Exactly. And the scale is just, it's staggering. If you look at the official high-severity vulnerabilities, the CVEs for huge projects like Chrome or Android, something like 70% of them are memory safety issues.
70%. It's an unbelievable number.
It is. And that's why we're looking at what systems like GrapheneOS do. They replace the standard Android memory allocator, Scudo, with something called hardened malloc.
So Scudo is good, But this is a whole different level.
It's a different philosophy. Scudo is robust, for sure, but
Yeah.
Hardened Malik takes a much more uncompromising stance on pure defense.
Okay, so if 70% of the big bugs are from this one area, we have to understand why. What is it about languages like C and C++ that creates this minefield?
Well, the thing is, it's a human error problem, and that's what makes it so tough. Unlike newer languages that handle memory for you, C and C++ make the developer manage everything manually.
And people just make mistakes.
All the time. It's not just about forgetting to delete something, it's about complex pointer math, managing buffers, just incredibly error-prone. One tiny mistake, one misplaced pointer, and you've opened a door for an attacker.
Okay, let's make this real. The sources talk about use after free. Paint a picture for us. What does that actually look like?
Right. Think of it like a storage locker. Your app uses a piece of memory of the locker, and then it's done, so it returns the key. The system marks it as free.
But the old data is still sitting inside.
For a moment, yes. An attacker is waiting for that exact moment. They quickly rent that same locker, that same memory space, and they put their own malicious code inside.
And when the original app makes a mistake and tries to use its old key one more time.
It doesn't find its old data. It finds the attacker's code and runs it. That's the exploit.
Wow. Okay, and what about a heap overflow? That sounds more like a brute force thing.
It is, yeah. Imagine your app asks for a bucket that can hold 5 gallons of water. A heap overflow is when the app tries to pour in 6 gallons.
And the extra gallon has to go somewhere.
It spills right over into the next bucket, the adjacent memory space, and it overwrites whatever was there. If that was critical data or instructions on what to do next, well, the attacker is now in control.
So we can't just rewrite all the C and C++ code overnight. That leads us to the defense. This is where hardened mallet comes in.
That's the idea. It's built on a philosophy of trading a tiny bit of speed for a huge amount of safety.
It's like a defensive layer. So let's get into the mechanics. The first one is called aggressive zeroing. You mentioned a performance cost, so what's the trade-off here?
It does add a tiny bit of latency, but it's a price you have to pay for security. The moment a block of memory is freed, that storage locker hardened malloc instantly wipes it clean, fills it with zeros.
So when the attacker tries that use after free trick.
They find nothing, just empty zeros. There's nothing to hijack, nothing to manipulate. The exploit just fizzles out. It fails safely.
Okay, and for the overflows, you have guard pages.
Exactly. To stop that spillover, hardened malloc puts these little unmapped memory gaps, the guard pages, between all the allocations.
So between the buckets.
Right. So if the app tries to overfill a bucket, the data doesn't spill into another bucket. It hits that empty gap, that unmapped wall, and the app just instantly and cleanly crashes.
Which all works alongside another layer, right? Randomization, the ASLR.
Yes. Address space layout randomization. Hardened malloc randomizes the Smith stuff, but the system-wide ASLR in GrapheneOS shuffles the big things like core code libraries way more aggressively than stock Android.
The analogy from the source was a library, right?
It's a great one. Think of a library where every time you leave, the librarian completely rearranges all the books on all the shelves, randomly. An attacker might know the title of the book they want, but they have no idea where to find it. They don't know where to jump to in memory.
Now, this leads to what sounds like a downside. Hardened malloc can make apps crash more often. But you're saying this is actually a feature. How is a crash a good thing?
Because a crash is safe. The real danger isn't the app stopping. The danger is when the app keeps running, but it's secretly being controlled by the attacker. That's a compromise.
That's remote code execution.
Exactly. When hardened malloc forces a crash, it means the exploit was caught. The attack was stopped dead in its tracks. The system chose to fail secure. You might lose a moment of stability, but you preserve the integrity of the whole system.
So a crash is a win for the defender. You've turned a potential system takeover into just a harmless, localized app failure.
But that's the whole game. It's an invisible shield constantly fighting off that 70% of vulnerabilities in the background.
It fundamentally changes the risk for the user.
Yeah.
It shifts the burden away from hoping every single developer wrote perfect code, which we know is impossible.
Precisely.
So here's a final thought for you to chew on. Since memory safety is clearly such a massive, persistent problem, how different would our digital world look if we just stopped building core operating systems with C and C++ set? What if we moved entirely to memory-safe languages like Rust? Something to think about until next time. All right, so we spent a lot of time on the theory behind security. Now we're going to hit the pavement, Get practical.
Right. This is about what you do before you even plug in a USB cable.
Exactly. We're looking at two fundamental questions. First,
Yeah.
which device do I actually buy? And second, maybe the bigger one, who am I protecting myself from?
And what's so critical to understand is that your security setup, its success or failure is decided right now at the point of purchase.
So let's start there. The sources are all clear on this. The foundation has to be a Google Pixel device.
Yeah, that's non-negotiable.
Why that specific hardware, though?
Well, it's about a combination of transparency and longevity. You need a device that allows you to unlock it and gets years of direct security support.
And that leads to the biggest rule of all.
The biggest rule, never, ever use an end-of-life device, an EOL device.
Even if the operating system like GrapheneOS is totally secure and up to date.
Yes, that's the trap, because the OS can't fix flaws in the hardware drivers.
You mean like for the Wi-Fi?
Well,
Or Bluetooth?
exactly. The OS can be a fortress, but as one source put it, the radio firmware underneath is rotting.
That's a great way to think about it.
And that's a vulnerability nobody but the hardware maker can fix. So you need those 5 or now 7 years of support you get with a new Pixel.
Okay, so you've picked a new Pixel. The next hurdle is actually buying it. This is where it gets tricky.
This is the hard stop. You have to buy a model that is OEM unlocked, sometimes called the Google edition.
And what's the big pitfall here?
The carrier models, the ones from Verizon or AT&T.
Ah,
You have to avoid them. They often permanently disable that OEM unlocking toggle in the settings.
and if that's disabled,
The whole project is impossible. You're done. You just bought a very expensive paperweight.
let's touch on the supply chain for a second. For someone who's let's say, a high-value target, a journalist, an activist, buying online links that phone's unique ID, the IMEI, to your name, your address, your credit card.
Yeah, it creates a digital paper trail.
How do you get around that?
You trade convenience for security, you go to a physical store, and you use cash. It decouples the device from your identity.
And that really sets up the biggest strategic decision of all, your threat model.
Right. Who are you hiding from? Because, secure is relative.
Okay, so let's take scenario one, the privacy seeker.
This person's adversaries are ad networks, Google, data brokers. They're not worried about a state agency kicking in their door.
So their setup can be a little more relaxed.
Yeah, exactly. They can do a standard GrapheneOS install, maybe even use the sandboxed Google Play for their banking app or something.
But then you have scenario two, the high-value target.
A completely different world. Their adversary might have forensic tools like Celebrate.
The kind of gear that law enforcement uses to pull data off a seized phone.
Yep. So their setup needs a total lockdown. No Google Play services, period. They need to run in LTE-only mode.
Why just LTE?
Because the older 2G and 3G networks are, well, they're fundamentally broken, full of security holes, and they also need to set up frequent auto reboots.
What does that do?
Every reboot wipes the encryption keys from the phone's memory. It makes physical extraction incredibly difficult if the device is seized.
So let's boil it all down for everyone. 3 things to do before you even spend a penny.
1, check the EOL status. Make sure you have years of support left. No rotting firmware.
2, make
Huh.
sure it's carrier unlocked. That OEM toggle has to be available.
And 3,
Yeah.
define your threat model. Am I hiding from advertisers or am I hiding from governments?
It's just wild that the installation process doesn't begin with software.
Not at all. It begins the moment you decide which phone to buy in which store. Get that wrong and you failed before you've even started.
And speaking of starting, next time we're going to dive into the actual technical steps. We'll focus on that web USB installer and the mechanics of finally flipping that critical OEM unlocking switch.
Okay, let's unpack this.
Let's do it.
Today, we're doing a deep dive into something pretty technical, but also increasingly important, enhanced device security.
Specifically, installing GrapheneOS.
Right. And we're going to focus on the recommended method, the web USB installer, because it's sort of democratized the whole process. You don't need to be a command line wizard anymore.
Exactly. But making it easier doesn't mean you can skip understanding the why. Our mission here is to really clarify that 3-phase sequence: unlock, flash, and lock.
Especially that lock part.
Oh, that's the whole game right there. That's where the security model really comes together.
And before we go one step further, the big, bold warning. This process will permanently, cryptographically wipe all data on your device.
No, going back. So back up everything you care about now.
Okay, so let's start with prerequisites. The very first hurdle.
And it's probably the #1 point of failure, It's the cable.
Just the USB-C cable?
Yep. It has to be a high-quality data cable. The standard charging cable you have lying around, it's probably not going to cut it.
It just doesn't have the data integrity for these huge system files.
Precisely. You're optimizing for data fidelity, not just power.
Yeah.
Then on the software side, you have to use a Chromium-based browser.
So that's Chrome, Brave, Edge.
Vanadium, if you're already on GrapheneOS. But yeah, Firefox or Safari, their web USB just isn't quite there for this.
Okay, cable's good, browser's open. What's next?
Now you have to tell the phone it's okay to be modified. You enable developer options.
That's the one where you tap the build number 7 times, right?
Yeah, that little trick. And inside there, you toggle on OEM unlocking. That's the master switch.
What happens if that switch is grayed out? I know people run into that.
Yeah. If it's grayed out, that's almost always a carrier-locked device.
Like from Verizon or someone.
Exactly. And if that's the case, you're unfortunately stuck. There's no simple workaround for that.
Okay, so assuming it's not grayed out, we've enabled it. Now we're at the point of no return.
The bootloader unlock.
Yeah.
The danger zone. You boot the phone into the bootloader. That's power plus volume down.
And then the website installer has a button that says Unlock Bootloader.
It does. And this is a really critical security point. The second you trigger that, the device performs a full factory reset.
Right then and there. Right after.
Immediately. It's a security feature. It prevents a thief from, say, stealing your phone and unlocking the bootloader to read your data.
So the unlock itself triggers a defensive wipe. That's smart.
It is. And you still have to physically confirm it on the phone screen itself.
Using the volume keys and the power button, so it can't be done by accident.
It's a final safeguard. Okay, so now the bootloader is unlocked and the device is wiped. Time to flash.
The website downloads the release, and then you just click Flash Release.
And the script does all the heavy lifting. It sends the factory images, bootloader, radio, the whole system. The phone even reboots itself into a special mode called Fast Boot D.
What's that for?
Fast Boot D is basically a deeper level mode for writing to the system partitions. But the main takeaway here is, do not touch the cable.
Don't even look at it wrong.
Seriously. If you interrupt it here, you have a very high chance of soft bricking the device. Just be patient.
All right, flashing is done. The phone boots up. So why do we need that final step? Locking the bootloader, what's the risk if we just stop here?
The risk is enormous. This final step is what separates GrapheneOS from, a lot of other custom ROMs. Locking reestablishes verified boot.
The cryptographic check.
That's it. It ensures the phone, every time it starts, validates that the OS is the genuine cryptographically signed version from GrapheneOS. An unlocked bootloader completely bypasses that check.
So without the lock, the whole security model is compromised.
Totally. Anyone could load a tampered OS. It's like building a fortress and leaving the front gate wide open.
So what does this all mean then? The WebUSB tool makes high-level security accessible. But the real insight isn't the tool.
Not at all. It's the sequence. Unlock, which performs that defensive wipe. Flash, to install the new system. And lock, to seal it all with verified boot.
That sequence is everything. It's the foundation.
But,
just because your device boots up doesn't mean the installation is 100% genuine or secure.
Which brings up a final provocative thought for you.
Okay.
How can you cryptographically prove that your device, hardware and software, is actually trustworthy after you've finished this whole process?
So you've gone through the whole process. You've successfully installed a specialized OS, something like GrapheneOS. But here's the big question, right? How do you actually know the download wasn't hacked or that the installation itself wasn't compromised somewhere along the way? I mean, the golden rule of security is always trust but verify. And that's our mission for this deep dive. To really understand attestation, we're going to look at how the Auditor app lets your device, prove its own integrity.
Exactly. And the foundational concept here is something called remote attestation. It's basically the mechanism that lets a device prove its identity and its current software state to someone else. And crucially, it does this without giving up any secrets. For a professional security posture, this is, it's absolutely non-negotiable. And this integrity, this proof, it's rooted entirely in hardware. Specifically, we're talking about the Titan M2 chip. This isn't just some software check that could be faked. The reliability comes from the fact that the Titan M2 is completely isolated. Even if the main OS gets, totally owned by malware, that chip is safe. It can't be forced to lie.
That's a huge distinction, isn't it? Hardware versus software verification. So when we talk about the certificate that the Titan M2 signs, what does it actually What is it actually guaranteeing? What are the bullet points?
It's providing 4 key cryptographic proofs. So it's attesting to, 1, I am a genuine Pixel device.
Oh.
2, I am running GrapheneOS version X, the specific version.
Okay.
3, my bootloader is verifiably locked. And 4, maybe the most important, I have not been tampered with since the last time I was verified.
So it grounds the whole chain of trust in the physical hardware.
Precisely.
So let's get practical. How does the auditor app setup actually work? I hear you need 2 devices for this.
You do. You need the oddity, that's your main GrapheneOS phone that you're checking, and then you need the auditor. And the auditor can be, just a regular stock Android phone. So the initial process is what sets up that trust. The auditor phone scans a QR code on the oddity, and that first time it reaches out to the Google Hardware Attestation Service. That service just verifies the signature is legitimate and is really coming from that Titan M2 chip.
And once that checks out,
Once that's verified, the auditor app stores a unique value. We call it the pinning token.
and that pinning token, and that's kind of the aha moment, right?
Yeah.
Because once the auditor has that, you don't need the internet for any more checks,
You got it. The devices are paired. It's all local from then on.
which enables things like downgrade protection, so you can tell if someone tried to roll the OS back to an older, more vulnerable version.
Yes. And that leads us directly to the really critical real-world benefit, evil-maid detection. So imagine you leave your phone unattended, maybe in a hotel room or a locker. When you get it back, before you even unlock it, you just pull out your auditor phone and do a quick local scan.
Because it's just checking against that locally stored token.
It's instant. If that QR code scan fails, that's it. That is your verifiable proof that the device was tampered with while you were gone.
And this ties back to that yellow warning screen people see on the very first boot with the super long hexadecimal number.
Your root of trust hash, yeah.
That's not a glitch then.
Not at all. It's
Okay.
the starting point for this whole security chain. The Auditor app is just confirming that the hash on the screen matches the official GrapheneOS signing keys.
Mm-hmm.
It's a confirmation, not an error.
So to pull this all together, what are the key takeaways for you listening? First, this verification is hardware-backed. It's all about that isolated Titan M2 chip.
Right.
Second, the pairing process builds a solid device-to-device chain of trust. And third, it gives you that instant downgrade protection and, physical tamper detection.
That really sums it up. This whole process concludes the foundational part, the installation. You now know the OS itself is sound. But, having that secure base just raises the next big question.
What happens inside the OS?
Exactly. What about when you start installing applications? So for our next deep dive, we're going to look at the application sandbox and how developers are using new tools like storage scopes to handle apps that demand, well, what used to be really invasive permissions.
All right, welcome back to the deep dive. So we spent a lot of time talking about, securing the operating system itself, hardening the kernel, locking everything down. But here's the uncomfortable truth. A perfectly secure OS is, it's basically useless if the apps you're running on it are the main way things get compromised.
That's it, exactly. It's like building Fort Knox, but then, every visitor gets their own personal safe that has a broken lock. You're still in trouble.
Right.
So today, our mission is to really give you a deep understanding of the Android sandbox. We want you to walk away knowing exactly how your device isolates apps.
So that a malicious flashlight app can't just go and steal your banking password.
Precisely. We're going to look at the Linux Foundation, the strict security enforcers, and how we can strengthen those walls to stop so-called sandbox escapes.
Okay, so let's unpack it. Where do we start?
It all starts at the very bottom. Android is built on Linux, and that's where the most basic security comes from. Isolation through something called discretionary access control, or DCE. And what's fascinating is how Android uses this. Every single application is treated as its own unique user.
Wait, so if I install WhatsApp, it's not just an app. The system sees it as a completely separate person, basically. It gets a user ID, like, say, 1005.
Exactly. And Signal might get a 1056. And by default, DC just means that user 1055 is physically unable to access the files or data belonging to user 1056.
Okay, so they're in their own little digital filing cabinets.
Think of it like that. It's a foundational wall.
That seems pretty solid. So if every app is its own user, why would we need anything more than that? What's the weakness?
The weakness is the Linux kernel itself. What if there's a vulnerability? Or what if an app finds some flaw that lets it trick the kernel into granting it access, even for a millisecond? That foundational wall, DIC, it doesn't guard against bugs in the kernel.
Okay, so you need a stricter referee. This is where it gets interesting.
That's where mandatory access control, or MAC, comes in. This is handled by C-Android, that's Security Enhanced Linux.
The strict parent.
That's a great way to put it. So if D-Day is the default rule that says, you can open your own filing cabinet, Linux is the strict auditor who steps in and says,
I don't care.
I don't care if you can open it. Company policy says you absolutely must not look at those specific files. It just overrules the basic user permissions.
And I know hardened systems like GrapheneOS, they really tighten these Linux policies, right?
Oh, absolutely. They take out a lot of the exceptions that are, often left in for developer convenience. They make that strict policy the default for everything.
So we have the user-based foundation and the strict auditor policy on top. But the biggest fear is still that sandbox escape.
Right. When an app breaks out of its little UID prison and attacks other apps or the OS itself.
So how do we stop that?
We harden the way processes are created.
Yeah.
So normally a new app process might fork from an existing system process, like Zygote. It kind of inherits its state.
It's like inheriting bad habits from your parents.
Exactly. And the danger there is that you could inherit a compromised or, a tainted memory space. Contamination.
Okay, so what's the alternative?
The alternative is exec spawning. This creates the new app process in a completely fresh, clean memory state. It's a guaranteed fresh start every time. It prevents that contamination from spreading.
That's a major one. What else?
The second big one targets an area hackers just love. Just-in-time compilers, or JIT compilers.
You see these in browsers all the time with JavaScript engines.
All the time, yeah. They generate code on the fly to boost performance, but that temporary, dynamically generated code, it's a perfect temporary window for attackers.
A vulnerability that only exists for a fraction of a second.
For a split second. So JIT hardening is all about restricting the memory permissions specifically for those JIT compilers. It makes it exponentially harder for an attacker to run malicious code they just created. It slams that window shut before they can jump through.
Okay, so let's bring this all back for you listening at home. The takeaway is that there are really 3 layers protecting you.
That's right. First, apps are all treated as unique users.
Second, Linux provides those mandatory strict enforcement policies over everything.
And finally, hardening methods like exec spawning and JIT hardening prevent system contamination and those breakout attempts. That malicious flashlight app stays locked in its cell.
Right.
Precisely. But, this raises an important question. If the sandbox works so well to lock everything down, what happens when an app legitimately needs access to your data, like your photo gallery app needing to see your photos?
That's the tension, right?
Yeah.
Security versus functionality. And that perfectly sets up our next deep dive.
Mm-hmm.
We're going to explore storage scopes, this brilliant concept of being able to essentially lie to an application by giving it an empty folder instead of your actual private data. Someone to mull over until next time.
Let's be honest, you're trapped. Every time you download an app, you face this permission nightmare.
Oh, absolutely.
In the standard mobile world, it's a binary choice. It's either allow or deny.
And if you hit deny,
the app just crashes. But if you hit allow, it gets everything. You just give up your privacy.
a zero-sum game.
Exactly. And our sources kept pointing to this problem, which led us straight to this feature called scopes.
A GrapheneOS exclusive.
Right. And it introduces this revolutionary third option, allow but restrict. We're diving in today because the research suggests this might be the single most powerful privacy tool you can have.
Yeah, and to really get it, you have to understand the risk of that initial allow. When an app wants storage permission.
Like a photo editor or something.
Exactly. It's asking for a permission, technically called read external storage. It just needs one photo from you.
But it doesn't take just one.
No. It gets access to your entire shared storage, all your downloads, your personal photos, your documents, everything. The scope is just massive compared to the actual need.
Okay, so let's get into the solution then. Storage scopes. The goal, as I understand it, is to run a risky app, maybe like Instagram, with 0 actual storage permissions.
Correct.
But still let it save and open a file. So how does the OS even pull that off? I mean, wouldn't the app just know it's been denied access and crash?
Well, this is the clever part. It's a masterful deception. The OS creates an illusion.
An illusion?
Yes, The app asks for permission, and the OS says, yes, you have storage access.
Ah.
But what it's really done is given the app a completely empty, totally locked down fake folder.
A fake folder. So I can actually trick an app into thinking it's running normally, but it's really just sitting in a sealed, empty room?
That's the aha moment right there. It sees nothing else on your device.
Wow. Okay, so what's my role in this? What do I, as the user, have to do to make this work?
And that's where the power shifts back to you. You have to manually drag just the specific file or folder you want that app to see into this scope.
So just one picture.
Just one picture. The app only sees that single item and nothing else on your phone. It means you can use these really intrusive apps without exposing your entire photo gallery.
That's huge for files. But what about my social graph? My contacts list is just as, if not more, sensitive.
And that's exactly why the source material also really stresses the importance of contact scopes. It's the same principle.
Right.
You know when you download a simple game and suddenly it demands to see your entire address book?
Just to see if friends are playing. It's ridiculous.
It is. And standard Android makes you give it everything. Names, numbers, emails, addresses, all of it.
So contact scope stops that.
It stops it cold. The app checks your address book and it sees an empty list. Nothing.
And then I choose.
You then selectively allow specific contacts, maybe just your spouse or one coworker, your entire business network, your kids' contacts. They all stay completely invisible to that app.
So if we connect these two ideas, we're really talking about data mocking, right? It sounds like we're running a digital sting operation.
That's a great way to put it.
We are lying to the app. We're feeling it just the bare minimum data it needs to function and nothing more.
Precisely. You're granting access to a tiny controlled piece of data, not to the whole file system, not to the whole resource.
And that's the key.
It is, because this lets those older legacy apps, the ones that were coded to demand these huge sweeping permissions, it lets them run perfectly fine and safely. It's a real escalation of user control.
So if we can manage storage and contacts with this kind of fine-grained control, what's next? The sources we looked at seem to hint there were other frontiers in this privacy war.
There are.
Next time, we really need to dive into how the same idea is being applied to things like your network and your phone's sensors, learning how you can create an effective firewall for specific apps and do it without ever having to root your device.
It's the next logical step.
Definitely something for you to consider exploring as you think about your own mobile security.
Okay, let's unpack this. Have you ever checked your phone's network usage and just wondered why your simple calculator or, a basic flashlight app has sent megabytes of data? That feeling is often justified. Our deep dive today is all about achieving what our sources call total isolation on your phone. And the core problem they highlight is, it's pervasive. On most standard operating systems, the internet permission is just given away automatically. And the critical part is you can't revoke it. Our mission here is to uncover the controls that actually stop this hidden communication.
And what's so fascinating is how certain systems, like GrapheneOS, which we're looking at, they tackle this by moving way beyond just a simple allow or deny. They restore this really granular control over things like networking and sensors, the stuff that's usually completely hidden from you.
And the first step, the one that everyone seems to love, is this network permission toggle.
Oh, absolutely. It's because it acts as a total iron curtain for data. It lives right there in the app's permissions page. When you flip that network toggle off, the operating system doesn't just tell the app no. It goes much deeper. It immediately creates a local firewall rule for that app's unique ID. It's called the UID right at the kernel level.
Okay, hold on. So why is a firewall rule for that specific UID so much stronger? I mean, couldn't a smart app just see the denial and, throw an error, force me to turn it back on?
That's the brilliant part. It can't. Because the block happens so low in the stack, the app never even realizes its packets didn't make it. They're just dropped before they ever reach the outside world.
So the app is effectively air-gapped.
Exactly. You can take a note-taking app and stop it from sending analytics. Or make sure your camera app can't upload location metadata. And the app still works perfectly offline.
This is where it gets kind of insidious, though, because it's not just the network we have to worry about. We have to talk about the hidden spies inside the phone, the sensors. We're talking about the accelerometer, the gyroscope, things you don't normally think of as spying tools.
Right. And the threat research here is, it's genuinely startling. If you leave your phone on a table, the gyroscope, the thing that measures rotation, it can actually measure the tiny vibrations in that table. Researchers have shown it can be used to listen to speech, or even more unsettling, to identify your keystrokes just from the microscopic movements as you type.
Wow.
So the defense strategy here is essential. First, the system limits the sensor sampling rate by default, which helps prevent that kind of high-fidelity spying. But the real control you get is a dedicated sensors toggle. You can just completely shut off access to all those motion and environment trackers for any app that doesn't truly need them.
And this idea of control goes even deeper. The system actually exposes what are normally these hidden internal controls, app ops, as simple user permissions.
And this is crucial for things like battery life and performance. App ops are just operations that are usually hidden away. They give you the power to block an app from using two key functions: keep awake, which is a huge source of battery drain, and also run in background. This is how you finally stop that one social media widget from just silently eating your battery all day long. You control its resources, not the developer.
So if we put all of this together, what does it actually mean? Our sources suggest that by combining this network permission toggle with storage scopes, that's the control that decides exactly which files an app can see, you can achieve total isolation. Imagine this. You install a gallery app, but you configure it so that it can only see 5 specific photos. That's it. And critically, it can't talk to the internet at all. That level of control just fundamentally changes the game.
And this raises a really important question for you, the listener, to think about. If a specialized system has to build these extreme explicit controls just to stop an app from doing something simple like keep awake, or to limit a sensor to stop it from listening in, what does that imply about the level of surveillance and resource abuse that's possible on standard phones that just lack these controls by default? It's really worth considering what kind of silent access your own device might be granting right now. So for the longest time, if you were a mobile user who cared about privacy, you had this impossible choice, right?
Yeah, exactly. It was a binary. You either got full compatibility, perfect app functionality,
Right.
but with, full surveillance from stock Android.
Or you went with a custom ROM for genuine privacy, but then, well, half your apps would just break.
And this is where GrapheneOS really changed the game. They looked at that and said, no, we can do both. And that's our deep dive today. Their breakthrough, sandboxed Google Play services.
The holy grail, it sounds like.
Pretty much. We're going to explore how they run Google's own code without giving it any special power.
Okay, so that's the mission. How exactly do they put Google in a box on your phone and make it a guest, not the landlord?
Well, to really get it, you first have to understand the problem on a normal phone.
The privilege problem, as you called it.
Right. On your standard Pixel or Samsung, Google Play Services isn't just an app, it's a system app.
Meaning it basically has the keys to the kingdom.
It has the keys, it acts almost like root. It can grant itself permissions, bypass your choices, access all your files, track your location, because it's woven deep into the operating system.
It doesn't have to ask.
It doesn't have to ask. And the GrapheneOS insight was, almost shockingly simple. They just said, what if we treat it like any other app you download?
Just a regular app.
Just a regular app. And they built what's called a compatibility layer. Now, this isn't just a container. It's a sophisticated lie.
A lie. What do you mean?
It intercepts every single request that Google Play Services makes. It tricks the service into thinking it's running with full privileges. But in reality, it maps all those powerful requests back to the normal Android permissions that you control.
And this is the absolute crucial point for anyone listening, right? This is zero privilege environment.
Exactly. It means Google Play Services has the exact same permissions as, a calculator app you installed.
Like Flappy Bird.
Like Flappy Bird, yeah. You can deny it network access. You can deny it location. You can deny it storage. And it is completely contained. It can't jump the fence and read data from your other apps. You are the boss.
Okay, but hold on. I have to ask the obvious question here. If the whole point is privacy, why install Google's code at all? Isn't that still a compromise?
But it's a practical one. I mean, we're aiming for a phone that actually works in the real world. And there are 3 dependencies you just can't really avoid.
Okay, what are they?
First, notifications. Almost every app relies on Google's Firebase for push notifications to work instantly.
Right, your messages and alerts.
Second is Maps. Your Uber or your food delivery app, they all plug into Google Maps APIs to function.
And the third?
Integrity checks. This is a big one. Banking apps, corporate apps. They use things like SafetyNet or Play Integrity to make sure your phone isn't hacked or tampered with.
And installing it is. It's nothing like the old days of flashing custom ROMs, right?
Oh, not at all. There's no complex flashing. You just open the GrapheneOS app, you tap install, and it just places 3 normal packages on your phone.
Just regular apps.
Just 3 regular apps. And the best part, because they are just apps, if you change your mind, you can uninstall them all in like 10 seconds. It's gone.
So when you tie this all together, that's really the killer feature, isn't it?
It is. You get, what, 99% of the functionality of stock pixel?
But with only a tiny fraction of the privacy invasion? Because you finally made Google a guest. You're the landlord.
And it all comes down to those 2 ideas, the zero privilege enforcement and that very clever compatibility layer.
It's a fundamental shift in who owns the data flow on your device.
Absolutely. And that actually leaves us with a final provocative thought for you to chew on.
Go on.
If we sandbox Google, and Google is what usually handles all the location services on a phone. How does your GPS still work? What invisible, privacy-safe system is now finding your location without any of Google's help? That's something to think about until the next deep dive.
All right, welcome to the deep dive. Today, we're really getting into what our sources are calling the single most sensitive piece of metadata your phone produces.
Your location.
Your location. And for most people, convenience means just trusting Google to know exactly where you are all the time.
Yeah, and that convenience has a name. It's Google Location Accuracy. And, well, what's happening under the hood to get that speed it's a little startling.
How so?
To get that instant lock, stock Android is constantly sending Google scans of your Wi-Fi networks, any Bluetooth beacons nearby. It's literally mapping your immediate environment to pinpoint you.
So that's the core privacy trade-off right there.
It is. So our mission today is to really unpack the GrapheneOS alternative. I mean, it's a system designed from the ground up to cut Google out of that loop using things like SUPL and GSF proxy.
Okay, so let's start there. An app asks, where am I? How different are the answers?
Fundamentally different. On stock Android, the answer is a mix. It's GPS satellites plus Google's huge database of Wi-Fi networks. It's fast, but you're handing over your local network map.
So GrapheneOS forces a return to what you might call, true GPS.
That's a great way to put it. Yeah, pure satellite triangulation. But you still need that assisted GPS, that AGPS, to make it work quickly without being invasive.
And how does it do that without just calling Google?
That's where SEPL comes in, Secure User Plane Location. It's designed to get that assistance data, the info that helps your phone find satellites faster without the network snooping.
So it connects to a different server.
Exactly. By default, it's a proxy server at grapheneos.org. It privately downloads the satellite data it needs. The crucial distinction is that it refuses to upload your local environment, your Wi-Fi, your Bluetooth. That stays on your device.
So we're choosing a slight delay maybe for a massive privacy gain. That seems like a worthwhile exchange.
It is, but you have to know the trade-off. Because we're not cheating with that local network data, getting that first lock indoors, it might take, say, 2 to 5 seconds longer.
A few seconds for total ownership of your movement history. I think most people would take that deal.
I would think so.
Okay, so that handles the network scanning problem. But what about the apps themselves? I mean, millions of apps are hard-coded to only ask for the Google-fused location provider. Shouldn't they just break?
Yeah. That's the second hurdle, isn't it? And this is where the engineering gets really, really clever. There's a component called GSF proxy.
GSF proxy, what does it do?
You can think of it like a brilliant double agent. When an app sends out that hard-coded call for Google's location service, the proxy intercepts it instantly. And it just redirects the request to the standard built-in OS GPS provider instead.
Wow. So the app gets the coordinates it needs.
Thinking it got them from Google's proprietary service.
When really it came right from the hardware GPS, and no data was sent to Google servers.
0. Not a byte. It creates this massive intentional blind spot in the whole surveillance architecture.
But there has to be a limit, right?
There is, and it's an important one. GSF proxy is perfect for apps that just need coordinates.
Right.
A weather app, for instance. But if an app needs to actually draw the map, the Google Maps tiles, then you still need to use Sandbox Place services for that visual part. The proxy only translates the coordinate request itself.
So to just pull all this together, GrapheneOS has built this three-pronged defense.
That's right.
You've got SUPL for private satellite data, a complete refusal to do any Wi-Fi scanning.
Yep, no local network uploads.
And then GSF proxy, the translator that keeps all your apps working without the privacy compromise.
And if you connect that back to the bigger picture, it shows that location privacy is, it's a solvable problem, but the source material points us toward the next unavoidable hurdle.
Which is?
Push notifications.
Yeah.
Even when you've solved location, essential apps like Signal, like WhatsApp, they often still need a connection to Google's ecosystem just to wake up and receive a message.
So you're still tethered in a way.
In a fundamental way. And it raises this really important question. If the basic infrastructure for communication is controlled by a third party, how much true control do we actually have? That's the challenge that's still out there. Welcome to the Deep Dive. So today, let's get into something we all experience but maybe don't think about, the push notification.
Right.
I mean, how does your email app, which you haven't opened all day, instantly ding the second a message arrives?
Yeah, how does it know? It's not running.
Exactly. So let's unpack this.
Well, you have to start with the fundamental problem here, what we can call the battery problem.
The battery problem.
Okay, just imagine if every single one of your apps, Signal, Discord, Proton Mail, Uber, whatever,
All of them.
tried to keep their own separate connection open to their servers all the time.
Your phone would be dead.
It would be dead in like 4 hours. The sources are pretty clear on that. It's just not viable.
So you need a single traffic cop, a single shared pipe for everything to go through.
A shared pipe. And for most of the world, that pipe is Google's FCM.
Firebase cloud messaging.
Exactly. Google created this really, really efficient system. Your phone keeps one connection open to Google, and they handle funneling all the messages down that one pipe to the right app.
Problem solved, right? It's efficient.
Efficiency is definitely solved, yeah. But there's a price for that efficiency.
There always is.
Even if your app is end-to-end encrypted, like Signal, using FCM means your phone has to maintain a constant open connection to a Google server.
Right, like mtalk.google.com or something.
That's the one. And that's where the privacy cost comes in.
So what's actually leaking? It's not the message content.
No, the content can be completely secure. The leak is the metadata.
Okay, define metadata in this context.
Google knows when you get a notification and, critically, which app is getting it.
But wait, let's play devil's advocate. For the average person, why is that such a big deal? So Google knows my bank app dinged at 9 a.m.
Who cares? Because metadata builds patterns. A notification from your bank app every Friday morning, that's your payday. A flurry of notifications from a dating app every evening. That says something about your social life.
So even without reading a single word, they're building a pretty accurate profile of your behavior.
A very accurate profile. And what's wild is that without this system, without FCM, a lot of apps they can't get notifications at all unless you literally have them open on your screen.
Which brings us to the big trade-off. We see this really clearly on privacy-focused systems like GrapheneOS, right? It forces you to choose.
It really does. You have option A.
Okay, what's option A?
You install what's called sandboxed play services. This lets FCM run, giving you great battery life and instant notifications.
But you still have that open connection to Google's servers.
You still have the connection. The metadata is still flowing.
And option B?
Option B is no Google services at all. And then apps like Signal have to fall back to their own systems.
Like WebSockets.
Exactly, WebSockets. The app basically keeps its own connection open 24/7, constantly asking its own server anything new.
Which kills your battery.
It has a significant impact on battery life, so you're making a very direct trade. You're trading battery power for metadata privacy.
So if FCM is this monopoly that leaks data, and WebSockets drains your battery, is there another way? What's the way out?
Well, this is where the decentralized movement has a really interesting answer. It's an open standard called Unified Push.
Unified Push. Yeah. The goal here is to break that dependency on Google.
Completely. The idea is so elegant. Instead of everyone connecting to Google, you choose your own notification server, your own distributor.
So I can use a public one like, what is it, ntfi.esh?
You could use that, or you could even self-host one on a server at home. Apps that support it, like Element or Tusky, they send their notifications to your server, not Google's.
That sounds like the perfect solution.
In theory, yes. But the analysis shows adoption is, it's strong in the FOSS community, the open source world.
But my banking app isn't going to use it anytime soon.
Don't hold your breath for your bank or Uber to adopt it, no.
So for most people, for now, it sounds like that sandboxed FCM is the most practical compromise. You accept the metadata leak for the convenience and battery life.
It's the compromise most people land on, yes. And that choice really gets to the heart of your own operational security strategy. So maybe the question for you to think about is this. Next time your phone dings, just ask yourself, is this notification I'm getting right now worth the little piece of metadata that Google just collected about my life?
What's that balance for you? That's a great thought to end on. Thanks for diving deep with us. We'll catch you next time. Okay, let's jump right in. For today's deep dive, we're going to unpack some really advanced security tactics. We're moving way beyond, the basic stuff and looking right at the OS architecture itself. Specifically, how GrapheneOS uses user profiles for some serious OPSEC.
Exactly.
Our mission here is to really show you how these profiles aren't just for sharing your phone with someone. They're a genuine high-security isolation mechanism.
That's the key. We're talking about running multiple, completely separate and fully encrypted instances of the OS on a single device. This isn't just changing the wallpaper. It's a fundamental cryptographic boundary.
Okay, so that's the big claim. How is this fundamentally different from, say, a standard profile on another OS? What's the technical foundation that creates that wall?
It's all about the encryption keys. It's actually pretty elegant. When you create a new profile, GrapheneOS just generates a completely distinct set of keys just for that profile.
A unique set.
A totally unique set. And that ensures true data isolation. Profile A simply cannot see the files, apps, or accounts in Profile B. They're cryptographically invisible to each other.
And that security architecture leads us to what I think is the operational genius here, the end session function.
Precisely. To get how powerful that is, you first have to understand the difference between BFU and AFU.
Before first unlock and after first unlock.
Right. BFU, before first unlock, means your data is encrypted at rest. Think of it like a locked safe. AFU, after first unlock, means you've put the key in and the data is now decrypted in the phone's RAM. The safe is open.
Okay, got it.
So when you hit end session on a profile, it instantly wipes that specific profile's encryption keys from the RAM. Poof. That profile immediately reverts to the BFU state. The safe is locked again, even if the rest of your phone is still on and you're actively using it.
That is a game changer. That capability enables the whole daily driver versus toxic profile strategy, doesn't it? I mean, I know my banking app is probably clean, but my social media feels like I'm handling digital plutonium.
That's the perfect mindset for this. You put the plutonium in a lead-lined box, you keep your main owner profile clean, minimal, just the essentials you trust. Then you segregate everything else. You could have a Google profile just for Maps and Uber, or a social profile for Instagram.
Wait, let me push back on that. If I install some sketchy app on that social profile, how do I know it can't just jump over when I switch back to my main one? How is it guaranteed to be stuck?
Because that crypto boundary we talked about holds firm. If that malicious app tries to steal your photos, all it finds is an empty gallery in its own profile. It can't even see that the owner profile exists. And crucially, if you end session on that social profile, those invasive apps are effectively dead. No background tracking, no battery drain, nothing until you choose to unlock them again.
Okay, that isolation sounds incredible for security, but what about just usability? Am I going to have to constantly switch profiles just to see if I got a work email?
No, and they thought of that. It's handled by notification forwarding. The system will tell you there's activity. You'll see a notification that says something like new email and then in parenthesis work profile. So you're aware of it, but the actual content remains hidden until you switch and unlock that profile. It's awareness without exposure.
That's smart. And what about storage? I'm not downloading the same huge app file 2 or 3 times for these different profiles, am I?
Correct. You can install an app in your main profile and then use the Install Available Apps feature to just push the base APT to the other profiles. Saves a ton of space.
So let's wrap this part up. What are the key takeaways for you?
I'd say there are 3. First, the power of encryption boundaries. Those unique keys are everything. Second, the tactical advantage of end session, that ability to instantly return a profile to an encrypted state. And third, the absolute isolation it provides for quarantining apps.
So what this all really means is that you can mitigate the huge risks from all these privacy-invasive apps without having to give up their functionality entirely. It's OPSEC meeting real-world convenience.
It really is. But it raises a very important follow-up question. If the isolation is this tight, how do you securely get the data you do want to keep out of the phone? Why is backing up a super secure phone so much harder than an insecure one? Next time, we're going to tackle that backup nightmare by looking at Seed Vault. All right, welcome back to the deep dive. Today, we're tackling something that I think a lot of people struggle with. This tension between having a truly secure private phone and the very real fear of losing all your data. I mean, a secure phone without a backup isn't secure at all. It's basically a time bomb waiting to go off.
It really is.
So our focus for this deep dive is Seed Vault. It's the open source solution you see in GrapheneOS and other secure systems, mainly because they just refuse to use the Google Cloud.
And that's the fundamental choice right there. A standard Pixel phone uses Google Drive, which is super convenient, but it's a privacy disaster. Google holds keys that can decrypt your data.
So they have a back door.
Well, they have a way in if needed. GrapheneOS just removes that possibility entirely. The responsibility is 100% on you. It's pure self-sovereignty.
Okay, so let's unpack that. What makes Seed Vault so fundamentally different? Let's talk about the core security feature.
It all comes down to client-side encryption, meaning the data is encrypted on your device using keys only your device knows before it ever goes anywhere. By the time that encrypted file hits your storage, it's already a locked box.
A completely unreadable blob of data.
Exactly. And that brings us to what I call the iron rule of Seed Vault. The one thing you absolutely cannot skip.
The 12-word phrase.
The 12-word recovery phrase, or mnemonic.
Yeah.
That phrase is your key. There is no other. You have to write it down.
And when you say you have to,
Yeah.
You mean there's no forgot my password, link, no customer support to call?
Nothing. If you lose that phrase, your backup file is, for all intents and purposes, just random garbage. It's like dropping your only key into a volcano. Nobody can help you.
The control is absolute then.
Sissy.
So, okay, you've written down the key, you've secured it. Now that encrypted data needs a place to live. The sources really recommend one method above all others for storage.
Cold storage. It sounds technical, but it's not.
It's just a USB drive, right?
Yeah, a physical USB-C thumb drive you plug directly into the phone. You write the backup, you unplug it, and you put it somewhere safe. That's it.
But that requires, a physical action. It's not the seamless, in-the-background cloud backup people are used to.
It's a trade-off. It's the highest security for a little bit of friction. You do have other options like sending the encrypted file to your own private server with Nextcloud or something similar.
Okay, so it seems pretty straightforward, but the sources also point out some gotchas. It's not as simple as Apple's iCloud, for example.
Not at all. And the biggest limitation is something called app opt-outs.
An app can just refuse to be backed up.
Yep. The developer can flag it as no backup. And you see this all the time with banking apps, and famously with Signal.
Right, because Signal has its own internal backup and restore process that you have to use instead.
Exactly. Its own encryption layers that Seed Vault just can't touch.
So this reliance on diligence, remembering to run a manual backup, dealing with apps that opt out, that feels like the biggest potential point of failure for the average person.
It is. And that diligence is critical because even automatic background backups can sometimes fail. The phone's battery optimization might just kill the process halfway through.
So what's the best practice?
Always, always perform a manual run now backup before you do any major system update, just to be sure.
So when you step back and look at it all, what's the big takeaway here?
The takeaway is that you're swapping convenience for genuine control. The whole system is built on this principle of self-sovereignty. You are the only one who holds the keys. You own the storage. It turns a backup from a simple sync into a private, personal vault.
The power is clear, but that need for constant diligence really underscores why you have to know what you're doing.
It does. And, that actually brings up the next logical step. If you've gone to all this trouble to own your data, you then have to secure the physical device holding the keys.
Because the phone itself becomes the target.
It becomes the highest value target. So the question you should be exploring now is, does your physical security match your digital security? And that leads you down the path of advanced threat mitigation. Things like duress PNs, auto reboot timers, all things designed for when the threat is physical. Something for you to explore on your own.
All right, so for today's deep dive, we're going into what is, pretty much the worst case scenario in mobile security.
The absolute nightmare.
Yeah, we're talking about physical seizure of your phone and then forced decryption. The whole rubber hose cryptanalysis threat.
It's a very real threat.
Yeah.
And our sources today cover the architecture built specifically for that kind of crisis. We're going to unpack 3 key features here.
Okay, what are they?
We've got the auto reboot timer, then duress pins, and finally the AB update mechanism.
Right.
It's all built on this principle of attack surface reduction.
Attack surface reduction. Got it. So let's start with that first one, the passive defense, auto reboot. Why is something as simple as turning a phone off so critical here?
It all comes down to the keys. The encryption keys.
Right.
When your phone's unlocked, it's in a state called AFU after first unlock.
Right.
And in that state, the decryption keys are just, sitting there in RAM.
And that's the vulnerability.
That is the vulnerability. It makes the device wide open to forensic tools, things like Celebrate that law enforcement and other attackers use.
So auto reboot is basically a dead man's switch. If you don't touch your phone for a while, it protects itself.
Exactly. It forces a hard reset, which kicks the device back into the BFU state.
Like before first unlock.
Before first unlock.
Yeah.
Now the data is truly at rest, fully encrypted, and those keys are gone from RAM. You can't get to anything without the password, which is backed by the hardware Titan chip.
And the sources say the default timer is, what, 72 hours?
It is, but the recommendation is to crank that way down to something like 12 or even 24 hours. That simple change makes a hacker's job exponentially harder.
Okay, that handles the device being seized when you're not around. But what about when you are around? When someone is standing over you, forcing you to unlock it?
That's where we move from passive defense to active, when we talk about the duress PIing.
Right.
And what's so fascinating about this is that it has to look like a mistake to the attacker. It's a totally separate PIing code.
So you type it in, and to them, it just looks like you fumbled your real password.
Precisely. But what you've actually done is trigger a secret self-destruct sequence.
And you can configure how much it self-destructs. Right.
You can. There are two main ways to set it up. Configuration A is for if you use, say, multiple user profiles.
Like a work and a personal one.
Exactly. You enter the duress PIing for your work profile, and it instantly deletes only that profile. It gives you some plausible deniability.
And configuration B.
That's the nuclear option. You enter that code, and it triggers a full, immediate factory reset. Wipes the entire device, everything's gone.
Wow, okay. That's some serious defense. So finally, let's talk maintenance. Because all the security is useless if a bad update breaks your phone.
A huge, huge problem traditionally. And this is solved by what's called the AB partition system.
AB. So 2 partitions.
Yep. Think of it like your phone has 2 identical copies of the operating system, slot A and slot B. While you're using the phone on slot A, any new update is silently downloaded and installed onto slot B in the background.
So there's no downtime.
0 downtime. And the running system is never touched by the update process.
So after you reboot, it just switches to the new updated slot B. But what if that update is corrupted? Isn't your phone bricked?
And that's the most brilliant part. If the system tries to boot from slot B and fails for any reason, it just automatically reverts back to the old known good version on slot A.
It just fails over.
It fails over seamlessly. It makes bricking your phone from a bad update nearly impossible. That resilience is key to long-term security.
So when you put it all together, this isn't just, Android without Google. This is a whole different security philosophy.
It really is. The whole architecture is built on those pillars we mentioned. Attack surface reduction with the auto reboot, memory safety by not leaving keys in RAM, and then hardware-backed integrity from the AB system and the Titan chip.
It's a strategy designed for when everything has already gone wrong, which leaves us with a final, I think, provocative thought for you, the listener. The sources basically pose this challenge. Your practical assignment is to maintain this high security posture while also living a normal digital life. So where do you draw that line between these amazing security tools and just, daily convenience, something to think about?